Hello students, welcome to Marine Engineering Tutorials. I am Atul Kumar Gupta and back with a new tutorial. Presently we are studying marine auxiliary systems and deck machinery. Today we have 10th lecture and the topic is shell and tube type heat exchangers. In this tutorial, we will first discuss about two-pass shell and tube type coolers. Then we will discuss about tube expansion arrangement. Next we will discuss about tube fixing with soft packing. Then we will discuss about shell expansion arrangement. Next we will learn about the regenerative condenser. Then we will learn about the shell and tube type compressed air inter and after cooler. Lastly, we will discuss about coil type inter and after cooler. Let's discuss these through the following slides. Two-pass shell and tube type cooler. The sketch shows a two-pass shell and tube type cooler whose construction is described below. It consists of tube stack made up of cupronickel or aluminium brass tubes and admiralty brass tube plates fitted into a steel shell. Tubes are usually attached to the tube plates by expansion and bell mouthing and provide a passage for the coolant. The tubes are attached between a fixed tube plate and a floating tube plate which are sealed at both ends of the steel shell and provide expansion at the floating end. Headers or water boxes surround the tube plates and enclose the shell. They are arranged for either a single pass or for a double pass of cooling liquid. A single pass or straight flow is common in small coolers. A division plate separates the coolant inlet and outlet chamber in a two-pass arrangement. Shell and tube type coolers for engine cooling water and lubricating oil were traditionally circulated with seawater, although central freshwater system is used nowadays. Cooling sea or freshwater is in contact with the inside of the tubes, tube plates and water boxes. Sacrificial zinc anodes are used when seawater is used as coolant to prevent electrolytic corrosion of the water boxes. Hot liquid enters the shell from one end, gives it heat to the coolant and leaves from the other end. Baffles give direction to the liquid being cooled for good circulation and efficient heat transfer. Baffles also support the tubes and prevent their sagging. Tube expansion arrangement. The sketch shows the attachment details of the tube plates between shell and water boxes with tube expansion arrangement. Fixed tube plate is sandwiched between shell and water box. Sealing of the tube plate with shell and water box is achieved by fiber gaskets on both sides. A safety expansion ring is sandwiched between shell and end cover. Sealing of the safety expansion ring with shell and end cover is achieved by synthetic seal rings on both sides. Floating tube plate rests on the seal rings and is free to move, thereby providing expansion and contraction allowance to the tubes. Two seal rings separate both the liquids and thus prevent their intermixing in case of damage to the seal ring, which is revealed by the external leakage through the telltale holes provided in the safety expansion ring. Tubes are usually attached by expansion and bell mouthing. Although another method which is not so common is described on the following slide. Tube fixing with soft packing. This sketch shows tube fixing arrangement using soft packings, which is rarely seen on the ship's heat exchangers, and the process is both cumbersome and costly. The advantage of this method is easy replacement of the tubes. In this arrangement, holes are drilled, counterbore and tacked to secure the tubes as compared to only drilling in conventional method. This is a complex method of tube fixing due to several processes required. Thickness of tube plate required in this case is also more as compared to conventional method. Tubes are then secured in both the tube plates with securing rings. Sealing between the two fluids contained in the shell and end cover is ensured by two number seal rings on either sides. Tubes are finally secured with a locking nut on either side of the tube. Tube expansion is facilitated by a floating tube plate. Shell expansion arrangement. Similar to the requirement of tube expansion, shell also require its expansion arrangement. This sketch shows the expansion arrangement for the shell. Central part of the shell is split in two or three sections, either at one or both ends, with small gap to provide expansion. Expansion bellow, as shown is attached between the two sections, which provides expansion or contraction allowance to the shell. Regenerative condenser. The sketch shows a two-pass condenser mainly used on steamships for auxiliary purpose. In a condenser, the fluid to be cooled is the vapor which undergoes the phase change as compared to a cooler where the liquid temperature is reduced. The word regenerative used here means that part of the energy in steam is recovered back after its condensation. Seawater is used as coolant for condensation of steam and effective operation of the condenser requires that the seawater is colder than the saturation temperature of the exhaust steam which results in undercooling of the condensate. Condensers used on motor ships do not have the regenerative feature. Degree of undercooling should be minimum to reduce the fuel consumption in the boiler and improve its efficiency. Regenerative ability of the condenser avoids this thermal loss. Seawater enters the water box from the bottom. Division plate in the water box allows the seawater to travel through the tubes in two passes. Division plate also separates the tubes in two sections. Seawater first travels through the lower tubes called the first pass tube and then turns in the other water box on the free end to travel to the upper tubes called the second pass tubes. Seawater finally leaves the condenser from the top and is discharged overboard. Water boxes are equipped with sacrificial anodes to protect them from galvanic corrosion. Baffles arranged in the second pass tubes help to accumulate air or non-condensable gases. Air or non-condensable gases are drawn by the air ejector which is used to maintain vacuum in the condenser shell. Steam from low pressure turbine enters the condenser shell from the top, impinges on the cold tube carrying seawater and gets condensed. Part of the steam is led below the condensing water through the central passage, which helps to reheat the condensate to reduce its undercooling. This steam acts as the regenerative feature of this condenser. The condensate finally collects in the condenser well. Condensate pump draws out the condensate from the outlet at the bottom of the condenser shell. A level controller is used to maintain the condensate level in the condenser well so that the condenser can function correctly and condensate pump does not lose suction. Condensate pump recirculates part of the discharged water back to the condenser valve. Makeup water is supplied to the condenser well from feed tank when the level is low. A safety valve or bursting disc protects the condenser shell from over pressurization. Shell and tube type compressed air inter or after cooler. This sketch shows the shell and tube type compressed air inter or after cooler of an older design. Cooler tubes are attached between tube plate and a floating tube header which forms the tube stack. This arrangement compensates for the expansion and contraction of the tube stack as the tube header is free to move. Tube stack is inserted into the cooler shell. Fiber gaskets are placed between both ends of the shell to seal against the coolant leakage. Air header is attached to the tube plate and an end cover on the other side of the cooler end. Sealing between tube plate and air header is achieved by an annealed copper gasket. Cooling water enters the shell from one side and leaves from the other side. Compressed air enters the header from top connection and leaves from the bottom connection after taking two passes through the cooler. A bursting disc is equipped on the shell which protects it from overpressure when a tube ruptures. Coil type inter or after cooler. The sketch shows a coil type inter or after cooler which has replaced the conventional shell and tube type cooler used earlier. This arrangement is very compact and provides saving of the space. It consists of a cast steel tube header. U-tubes are attached to the tube header which automatically compensate for the expansion and contraction. As tube ends are not accessible, their cleaning is carried out chemically. Header is attached to the compressor jacket with a fiber gasket. U-tubes remain surrounded by the jacket cooling water. Cylinder jacket is equipped with a bursting disc to protect against the over pressure. Compressed air enters and leaves the tube header from the respective connections. Sealing at the air connection is provided by annealed copper gaskets. This completes the study of shell and tube type heat exchangers. This book is written by me and covers all the topics as per the syllabus specified by Indian Maritime University. It clarifies the concepts with simple illustrations. The book also provides answers to all the questions which have appeared in the examination conducted by Indian Maritime University. The book can help the students in preparing for the exam and also to work on ships, auxiliary systems, and deck machinery safely. Hope that you have liked the lecture. You can write your feedback in the comment box. If you have liked the tutorial, you may share it with your friends. You may subscribe to the channel for getting notification about the new tutorials. I will be back with a new lecture shortly. Thanks for watching till the end.